Let's now explore the oscillator module in BEAP. We can also call this a VCO, a voltage controlled oscillator. I'm working with the patch I created in the previous video, so we're going to continue adding to this. I'm going to add some scope modules, so let me unlock this patch, click on modules over here, and under the BEAP category, as we've seen before, I'm going to scroll down to scope here, and let's load in this voltmeter. I find this to be very helpful to understand a lot of what is happening inside a BEAP. Now across board, whenever you're working in the modular synthesis world, be it virtual or analog, it's all about voltages and manipulation of those voltages. So going back to these two outputs that I've already explained, let's take this gate output and plug it into this voltmeter. This voltmeter has a range of -5 volts to 0 in the center here, and also goes up to +5 volts. Let's ignore this number over here. Alright, so I'm going to lock the patch, and when I play a note, you obviously still hear the sound, but let's not focus on the sound right now. Let's take a look at the voltmeter. When I play a note, you can see the value on the voltmeter jumps up to 5 volts, and as soon as I let go, it comes back down to 0 volts. So this again further clarifies how gates work. So basically an on-off switch. Let's try unlocking the patch and connecting this cable to this output here, 1 volt per octave. Now you can see it's already off center here. Let me lock the patch and play some different notes, and you can see how that voltage value keeps increasing. And that's what's defining the pitch of the oscillator. And it stays there, it doesn't jump back to 0 like the gate output. Alright, so that's our 1 volt per octave output. Okay, so what if I was to connect this to the oscillator's output? So let's take the output from here and plug it in here. Now, it looks like it's jumping around pretty fast. This voltmeter is not quite designed to handle audio rate signals. Audio rate signals are signals that are moving at a much faster rate. So let's not do this. Let's use another scope. I'm going to click on modules here again, and same under the scope category, let's load in one that's literally called scope. Let's make some room for this one. Now I'll plug the signal output from the oscillator into the scope, and now we can see our actual signal. And look at that, it looks like a sawtooth wave, the one that's being selected. If I lock the patch, change the waveforms, you can see that the resulting scope changes. Now, even though we're not playing anything, the output is still active, and that's a very important thing to understand because that's how oscillators work. They're always outputting a signal based on whatever pitch you play. And as you can see, the scope is also updating to show the changes in pitch on this waveform. Now, what if I was to plug this over here? And now you notice that the signal is completely killed. So a VCA is doing that, it's killing the signal. And based on this CV signal, we will output, or we'll hear the output of the VCA. So now when I play a note, I'm generating that gate signal that goes into the VCA, tells the VCA, hey, we need to bump up the volume, and we get our signal. And you can see the resulting square wave. Change the waveform, and we see and hear the resulting changes.